This is the 18th video of the lecture series Optimization using Excel. And in this video, we are going to discuss another type of network flow model that is called the Travelling Salesman Problem. And we will use integer programming method to solve this Travelling Salesman Problem using Excel. So as we had discussed already in our video number 13, a traveling salesman problem can be defined in this way. Actually, there is no particular source or sink node in this case. The movement starts from just one node and progresses to other nodes, and the defining parameter is that one particular node is visited only once, and then all the nodes are visited, and at the end of the flow or the movement, the person or the flow unit that has started movement comes back to the original home position. So one common traditional example of traveling salesman problem is the newsboy problem. Like the newsboy takes the bunch of newspapers from the depot or from the distributor, and then he goes to various customers residing in various locations, and after he dispatches all the newspapers, he comes back to the depot or the distributor and then collects his payment. So in this way he visited all the nodes but just once, not repeatedly or not by any zigzag movement, and then comes back to his home position. So that means there is a complete circularity or roundness in the problem. That means it starts from one point and terminates in that particular point and visits every other nodes in the path and never visit a node, that is never visits a node twice. So that is the definition of TSP. Another example, little non-classical example is look at this CNC drilling machine. This drilling machine does it drilling in particular job in various locations. There can be several locations at various positions, and the drilling machine is supposed to drill in all those locations. So the drilling machine will start from one particular home position and drill all the holes and come back to the home position again. So in that way also it is a traveling salesman problem. So as we had discussed already, the one method heuristics, there are several heuristics. One heuristic is nearest neighbor algorithm, and the optimization models that are available to us are, one is nonlinear models, another one is integer programming models. So in this video we are not going to discuss the nonlinear part of the problem, nonlinear programming we will not discuss here. We will discuss only the integer programming part in this problem. So to understand it well, let us consider this particular problem. It is taken from some book, so they are writing problem number 46 and all, you can ignore that. So the problem is pretty simple. A particular school is there, and they have one school bus, and they pick up students from the 4 locations. These are the 4 locations, and they starts from school and come back to school again after visiting these 4 locations. Now in which order they will visit these locations so that the total distance is minimized, that is the problem to be solved. So as always, let us first try to see how to formulate it algebraically. So you see here I have repeated this particular network model or the distance matrix here. What is the difference? Difference is that in the problem they had given you the network in a unidirectional way, like considering the symmetry, only this portion of the network they have given. So I have assumed the same distance is available in the backward movement also. That means there is a complete symmetry. So that is why I have completed the entire table in this way. For example, this is 6, 29, 24, 10, and I have taken the transpose of that, that is 6, 29, 24, 10, and in this way I have completed the entire table. Now what is the decision variable? Decision variable is again xij, that is xij is a binary integer which is equal to 1 when the arc from node I to node j is selected in the network, and xij is equal to 0 otherwise. And then what is the objective function then? Objective function is pretty much simple. You take the xij and multiply that to the corresponding cost element, the costs, and then sum it up. So that gives you the total distance or total cost which is to be minimized. Okay, now come to the constraints part. Constraint part. So there are basically three types of constraints. First of all, try to understand this, how these constraints are developed. So the first set of constraints is this. So what is the description? Description is only one exit from node I. So suppose there is a node and we have already defined the problem in this way that the node will be visited only once in the network. So therefore there is only one exit from any particular node. So for example, if you take the node 0, so how many exits are possible? 0 1, 0 2, 0 3 and 0 4, and we are saying that only one exit we will allow from a particular node. So therefore the sum should be equal to 1. Similarly, from node 1, 1 0 is possible, 1 2 is possible, 1 3 is possible, and 1 4 is possible. These are the possible exits from node 1. So if you add them, the sum should be equal to 1. Why? Because we are only allowed to one exit from any node. So from node 1 also. In this way, all the 5 nodes are written. And please note that you should always remember the nomenclature of the nodes. For example, node 0 is for school. So for the home position, which is the school in this case, we define node 0, and from starting from 1 to 4, we have defined these particular locations as the node numbers. Okay, so this was the first set of constraints. What is the second set? Second set is there is only one entry to each node. So as you have seen that only one node can exit, so is true for entry also. So for example, any node I is there, you will have only one entry. So for example, you take the example of node 0. So entry can be from 1, from 2, from 3, from 4. So x10, 20, 30 and 40. So the sum should be equal to 1. Similarly for node 2, there can be x02, x12, x32 and x42. If you add them, the sum should be equal to 1. So this is the second set of constraints. Now this is not sufficient. There will be a third set of constraints also, because you see, you enter a node and you exit from the node, that is okay. But what will happen if there is an intermediate node? You enter here and exit from here, and then again you enter here in the previous node, and this goes on. So there are other nodes also in the network. There are basically 5 nodes are there. So this should have happened. This type of network should have happened. But if you just go by these two sets, then nobody is stopping you from having this type of network. So for example, I start from here, I cover these 3 nodes and complete the tour. So this type, if we want to eliminate these type of possibilities, then we have to write what is called is sub-tour elimination constraint. So these type of tours are called the sub-tours, which are to be eliminated, and for that we use a special kind of constraint set that is called Miller, Tucker and Zemlin MTZ constraints. Now in this video it is very difficult to explain for me how these constraints are actually working, but for the time being you just assume that if we implement this type of constraints, then it eliminates all kinds of these subtour possibilities. So what is the constraint? The constraint is written in this way: ui minus uj plus n into xij is less than or equal to n minus 1. And what is n? N is your number of nodes minus 1. Number of nodes minus 1. So how many nodes are here? You see 5 nodes are here. So 5 minus 1, that is equal to 4. So in your case, in the particular this problem, n is equal to 4. And what is ui and uj? These are another set of decision variables. ui uj are another set of decision variables which are not only greater than or equal to 0 but also integers. So uij are positive integers which are decision variables also. So you implement this type of constraint, and if you write in expanded form in particular to this problem, this will be written like this. So ui minus u2 plus 4x12 is less than or equal to 3, and similarly all these. So in this way the entire formulation will work. Obviously there are two more constraints. One is your xij should be a part of your binary set, and another one is ui and uj, they are greater than or equal to 0 and positive integers. So these two are also applicable here. Otherwise this is the entire algebraic formulation. Now we have completed the algebraic formulation. Let us move to the Excel sheet to see how this can be implemented in Excel. So this is my Excel sheet. Please note that these are my node numbers, as you can see here. This is the from to chart, like what is the movement from to. So from which node to which node movement. This is a set of decision variables. Remember xij. These are the xij's, and I have told you already that we have another set of decision variables ui and uj. So you have 4 uij like u1 to u4. This is another set of decision variables which will be populated here when we'll run solver. And this is your uh, cost matrix. So these are the unit costs of movement. This is also written here. And note the calculations. If we do the column wise sum, this is the basically this is the demand of each node, and if you do the row wise sum, this gives you the uh, supply or the capacity of each node. And if you calculate the sum product of these xij and your cost figures, this will give you the total cost, which is the objective function. Now please note one thing very carefully. Note these yellow color cells. Note that in our algebraic formulation there was no scope of x11 like x11 or x00 or x22, x33. This type of variables were not present because absurd. These were absolutely absurd about defining these variables. Like x11 means almost nothing, like starting from 1 and going to 1 again. So it does not mean anything meaningful. But in case of Excel, you see, we will not enter the decision variable xij individually. So in solver, when we enter in solver, we will enter this as a complete set. Like we will select this entire range all at once. So therefore, it is not possible for us to eliminate the entry of these yellow color cells. Although they don't have any meaning, any physical meaning, we are bound to enter them as decision variables in solvers. So now what to do? If you enter, there is no problem. Only thing is when you run the solver will anyway minimize the entire objective function. So since these are zero cost cells, it will make this one, these entries equal to 1 and total cost equal to 0. So that is not what we wanted. So now the way out from here is you just copy these cells again here, like b2, c3, d4, e5 and F6. You just take it down here and explicitly define this to be equal to 0 in solver. So we will see that we will enter the values, and now come to this part of the entry. Here we have implemented the Mtz constraints. Please remember the Mtz constraints that we discussed already in the slide. This is the implementation of Mtz constraints. So I have taken Uij decision variables here and also copied here as a transpose. Like I have taken B22 here, then B23 here, B24 here, and B25 here. Why? Because I want to write it little sophisticatedly so that it can be copied from row wise downwards. So for example, if you copy it, if you just drag it from top to bottom, it will replicate. Like you don't have to type it for every cell individually. So that is how this ui minus uj constraints are uh, written here. If you follow the formulation, you can understand how these constraints are actually entered here. So this is all about the formulation part. Now come to the solver menu. So go to data solver. Here what are the what is the objective? Objective is this sum product formula, which is the total cost, which has to be minimized. And then which variables are we going to change? Our decision variables. These are this one. Now see, again we have decision variable ranges disjoint here. So what do you do in case of disjoint sets? You put a comma and then again enter this particular set. I repeat once. You first enter the first set of decision variables, then put a comma and then again the second set. In this way you can enter both the ranges in this particular box, and then add constraints. So the total that comes out from each node should be equal to 1. We discussed already in the algebraic formulation, and these totals that goes into the each node, that should be also equal to 1. We already discussed the first two types of constraints, and these are our Mtz constraints. What should be the right hand side? Right hand side you can see here 3. So you enter 3 here, and most importantly these all decision variables, this will be binary, so enter that, and this will be integers. So add integer here and add. So once this is done, this is complete, and make sure that this is simplex LP, and then go to solve and click on it. So see, as we discussed earlier, if you don't explicitly define these 5 variables as 0, the solver will make them equal to 1 and report your decision objective function equal to 0. You see it is 0. So this is the error of the formulation, which we will correct. How we will correct? We will enter another constraint. You see I have taken these 5 cells here, so I will explicitly define them equal to 0 and add it there, and then again solve it. Now this is the final solution of this problem. So what is the solution? You just follow the ones here. So from node 0, where is it going? From node 0 it is going to 1. From 1, where is it going? It is going to node 2. So from node 1 it is going to node 2. From node 2 it is going to node 3. Pretty simple. It is going to node 3, and from node 3 it is going to node 4. From 3 it is going to node 4, and from node 4 it is going to node 0. It is going to node 0. So this is the complete path. This is the complete path. The traveling salesman optimal solution is 0, 1, 2, 3, 4. This is the optimal path to be followed. And what is the total cost? Total cost it is 56. So this is the solution. using integer programming and Excel. And now let us come to the slide once again. So as I have told you earlier also, there can be two methods of solving a traveling salesman problem. One is integer programming, another one is non-linear models. Both has some advantages and disadvantages. So in case of integer programming, what is the main advantage? Main advantage is it will give you the global optimal solution. So there is no question that whether any better path can be derived from the network or not. It will always give you the best solution, the global optimal solution. Whereas in case of non-linear model, there is no such guarantee. Like it will give you a good solution, it may give you the best solution, it may give you the global optimal solution, but there is no guarantee. It will give you a local optimal solution. There is a chance, very high chance although, that it gives you the global optimal solution, but again I am saying that there is no guarantee. And what is the advantage of nonlinear model? Main advantage is the simplicity. We have not discussed it yet, but when we will discuss the nonlinear models, we will see how this particular problem can be solved using evolutionary solver, which is a nonlinear solver. And setup is also easy. The problem is also small, and uh, solution is also easily obtained. And whereas the integer programming is can be quite complex. You see, in this case, we have just if you just monitor the number of nodes and the number of constraints. In this particular problem, you had you just had 5 nodes, and you landed up into 24 constraints. If you have 6 nodes, then if you will have 32 constraints. And in this way, if you just have 10 nodes, you will see that you will have to write 92 constraints. So in an actual network, 10 nodes is like nothing. It is a very common situation that you will have 10 nodes only. But for only for those 10 nodes, if you have to solve 92 constraints, then it is a very complex story. And it is better that you go for a non-linear model. So for example, if the network has 20 such nodes, then you can imagine how many constraints will be there, and most probably your solver will fail to solve, because in your free solver in Excel they have only given you the limitation of 200 constraints, so that will obviously fail. So that is the most pressing disadvantage for the integer programming models in this case. Otherwise, for small problems, you can obviously use it because it is, of course, most robust method. So that's all about traveling salesman problem using integer programming. And from the next video onwards, we will discuss the nonlinear models, and obviously one of them will be traveling salesman problem using evolutionary solver. So then we will see how this problem can be solved in using nonlinear approach also. So until then, goodbye and thank you very much for listening.